Let's look at a few examples for near ideal and non-ideal solutions here, and try to find some patterns so that we'll know what considerations to take into account while predicting whether a given solution is in close agreement with Raoult's law, or whether it exhibits a positive or negative deviation from this law. So one classic example that you will come across is that of benzene and toluene. Benzene and toluene. So benzene looks like that, and toluene is nothing but methyl benzene. So this will look very similar, except it has a methyl group. So these two liquids in fact form a near ideal solution. That is, when they are mixed together, their partial vapor pressures are in close agreement with Raoult's law. So if you look at it, both of these are non-polar molecules. So both are non-polar. So that's an important observation. And they're not very different in terms of their sizes. In fact, they have very similar physical properties. So similar, not very different sizes. Similar physical properties. Of course, their chemical reactivities can be really different, but similar physical properties. What else? What else do we notice about them? So the fact that both of them are they're both non-polar, the only intermolecular interactions that you can think of between these two molecules, so when we consider A-B sort of interactions, will be London dispersion forces. So within benzene as a liquid and within toluene, you have London dispersion forces, and even when you mix them together, that is the only intermolecular interactions they have. So London dispersion forces. These will be the intermolecular interactions. All kinds of interactions, AA, BB, and AB. So there is no obvious reason here why when they're mixed together, they should have much stronger AB interactions or much weaker AB interactions than AA or BB. So for all these reasons here, these two liquids form a near ideal solution. Near ideal solution. So clearly there is no reason for an obvious deviation from Raoult's law. Let's look at another example. That of acetone and ethanol. So let's see what we know about these molecules. So acetone has a carbon double bonded O and then two methyl groups, and then ethanol looks like that with the OH group. So when you look at these molecules, the observations that we can make are both are polar molecules. Both are polar. So in acetone, you clearly have a dipole because you have two lone pairs of electrons on oxygen that are not part of this double bond here, and because of which this acts as the negative end of the dipole. In ethanol, of course, because of this polar OH bond, you're going to have an extensive network of hydrogen bonding within ethanol, liquid between the ethanol molecules. So in case of acetone, since it's a polar molecule, the attractive forces between acetone molecules will basically involve dipole-dipole interactions, and that's how those molecules are held together. The acetone molecules do not have hydrogen bonding between themselves, but they do have these dipole-dipole interactions. So you have extensive hydrogen bonding in ethanol, and London dispersion, dipole-dipole interactions in acetone. So now what happens when you mix these liquids together is that the polar acetone molecules actually create AB interactions that are much stronger than, you know, the interactions that you find within acetone or within ethanol. So AB interactions, so the negative end of this dipole here has a strong attraction to the positive end of this dipole here, which is hydrogen. So this actually makes this these AB interactions, AB type interactions, much stronger than AA or BB. So because of this, what happens is when they are mixed together, these molecules are sort of stabilized in the solution phase, and they find it more difficult to get out into to escape into the vapor phase. As a result, they exhibit lower partial equilibrium vapor pressures than what they would in case of ideal solutions. So this mixture, the solution exhibits a negative deviation from Raoult's law. I have one more example here before we end this video. It is that of carbon tetrachloride, CCl4, and methanol. So what do we know about CCl4? So this molecule here is non-polar, and why is that? Because though the CCl carbon chlorine bonds here, all of them are polar bonds, because chlorine is highly electronegative, we know that. But what happens is if you have polar bonds like this that are symmetrical, I mean that are of equal polarity but point in opposite directions, they cancel out. So as a result, the molecule as a whole is non-polar. And so the only interactions that you could think of here between carbon tetrachloride molecules it's going to be just London dispersion forces. On the other hand, methanol is a polar molecule. So this is clearly a polar molecule. Let me just draw this out here. You clearly have a polar OH bond, and again you have a negative end of the dipole and a positive end of the dipole. So this is clearly polar. So then, as with any other alcohols, methanol is going to again have an extensive network of hydrogen bonding. So extensive hydrogen bonding in methanol. And we said that since carbon tetrachloride is non-polar, the only interactions there are the London dispersion forces. So the question now is, what happens when you actually mix these two liquids together that are so different? One is a polar molecule, the other is a non-polar molecule, and their sizes are quite different too. I mean, because of chlorines here, this molecule is much bigger than the methanol molecule. So in fact, when you form a solution with these two liquids, the non-polar carbon tetrachloride molecules actually interrupt the hydrogen bonding network in methanol. So and the lighter methanol molecules have much weaker London dispersion forces than these heavier carbon tetrachloride molecules. So as a result, these AB interactions here are much weaker than AA or BP interaction. So these AB interactions actually do not have a stabilizing effect like they do in this case, in case of acetone and ethanol. So here they are much weaker, AB interactions much weaker than AA or BP. So as a result, what happens is, because of this disruptive influence on each other, these molecules in fact find it easier to escape from the liquid phase into the vapor phase. So the resultant partial equilibrium vapor pressures of both carbon tetrachloride and methanol are going to be higher than what you would expect for an ideal solution. So in this case, you have a positive deviation from Raoult's law.